Our project that we are looking into is chemical vapor deposition. While that is a large collection of words, the idea is actually fairly simple. It is putting a plastic coating onto a bag. Chemical vapor deposition, or CVD, is the process where a polymer is formed around a product, such as a bag of chips, through some chemical reactions. Deposition may sound complicated, but in reality, it's as simple as a gas becoming a solid without having to turn into a liquid first. The deposition we are focusing on requires a gaseous compound, our chemical vapor, to attach itself to a surface that needs to be polymerized. When mapping out the deposition process, we are going to focus on 4 different chemical reactions that come into play. We'll be modeling how the surface and each reactant will change over time, observing and recording the changes in their rates and concentrations. Some possible alternative CVD modeling can include looking at the specific shapes of the molecules and their individual movements, though these can become extremely intensive calculations, so they will not be our current goal for observation.
The 4 reactions we are illustrating when looking into CVD will each have its own reaction rate that we will be changing throughout the modeling process. We will be looking at chemical reactions on a microscopic level, focusing on how each chemical reaction forms an essential compound for the polymer creation process. The chemical reactions involved in the formation of our polymer are S plus A going into SA, where S is the surface site, A is the gas phase adsorbate, and SA is the adsorbed species. SA plus 2O2 going into SiO2 plus 2H2O, where SA is again the adsorbed species. SiO2 plus A going into AO plus H2O, where A is still the gas phase adsorbate, and AO is the adsorbed species of Si. And finally, AO plus O2 going into SiO2 plus H2O, where AO is still the adsorbed species of SiO2.
These equations illustrate how the polymer is formed, but we will also need to see how each component changes over time as it is being used in laminar flow. The equations expressing the different components changing over time are expressed as:
Each is a different differential equation illustrating one component from each reaction. These components are the S, SA, SiO2, and AO. We just threw a lot of equations at you, and if you're like me, you completely ignored them because you don't want to think about the math. The best way to understand this process is by visualizing what's happening. The first step is our surface wanting some gas. The gas that attaches itself is silane, or SiH4, and wants to attach itself so bad it's willing to become a solid to do it. Then, the surface with its gas buddy forms a polymer, being silica, after some oxygen is introduced to the mix. After the silica is formed from that surface gas and oxygen mixture, some more of that silane wants in on the action, illustrating our third chemical reaction, where some of the silane and silica react to form an adsorbed species of the two and some water. Finally, oxygen is still being introduced, so the adsorbed species formed in the last chemical reaction reacts with that O2 to form more silica and water. Now, those differential equations are looking a lot less complex. Now that we have both the chemical reactions and equations illustrating how each substance changes over time, we need to go over to MATLAB to perform the experiment. Since we are dealing with multiple differential equations, we mapped out our code to solve them as an IVP through the ODE 45 function. We have the concentrations of all necessary compounds, especially focusing on both the silane and oxygen, and the equations describing how each of these concentrations change along the surface of the material over a time period of T equals ln space 0, 100, 100. The variable that we are choosing to manipulate through this project is the reaction rate itself, to better understand how each K1, 2, 3, and 4, affects the concentrations of each compound throughout the deposition process. After running the code, we came to some conclusions regarding how each compound is formed. One takeaway we had was that the adsorption rate was heavily dependent on how much adsorbate was present, in this case being the silane that was initially needed to bond to the surface. We also noticed that other factors, such as the buildup of water caused by 3 of the chemical reactions will need to be dealt with when it comes to performing CVD in the real world. This can be done by installing a compartment that allows for proper draining while the process is underway.